Hello everyone, welcome to my video presentation. Today I will be talking about the research work that I did during my master's program at LJMU. Point cloud registration is the problem of aligning the corresponding points of two 3D point clouds, referring to the same 3D object. The challenges include dealing with the noise and partial match of the real-world 3D scans. For non-rigid object, there is an additional challenge of accounting for deformations in the object's shape that happen to the object in between the two 3D scans. Depending on the type of environment, extended reality experiences can be classified into two categories: virtual reality and augmented or mixed reality. In virtual reality, the environment is computer generated, just like in computer games. On the other hand, in augmented or mixed reality systems, virtual objects are rendered into the real environment around the user. The headset is see-through and the user can interact with virtual and real objects with the identical hand gestures. Problem statement. In this project, we aim to study the problem of non-rigid partial point cloud registration for mixed reality applications. We focus our attention on a special class of non-rigid deformations that happen in rigid objects with parts that move relative to one another about joints. Example, robots with hands and machines with hinges. Aims and objective. 1. Implementation of baseline. Implement the current state of art point cloud registration algorithm. 2. Real-world evaluation of baseline. Evaluate real-time 3D point cloud registration for deformable and non-deformable objects in uncontrolled real-world settings in the presence and absence of distraction and with varying level of noise. 3. Identify and mitigate bottlenecks. Identify and mitigate any causes of drift or misalignment and potential bottlenecks slowing down the inference pipeline. Significance of the study. Education. Immersive lessons in topics like science, history, and geography are more engaging, memorable, and enjoyable by the students. Manufacturing. Mixed reality is changing the way design, training, repair and maintenance is performed in the manufacturing industry. Thanks to mixed reality, it's now possible to get remote hands-on assistance with repair and maintenance of precision engineering components. Healthcare. Mixed reality devices are regularly used for teaching anatomy to medical students. MR has also made it possible to overlay medical scans like MRI to a patient's organ for guiding the surgeons in the operation theater. Literature review. Feature extraction. The first step towards feature extraction is defining the neighborhood of each point. For example, spherical neighborhood, cylindrical neighborhood, parametrized neighborhood, which has the ability to control the scale at which local 3D structure must be encoded. The next step is extracting local 3D geometry features to attach semantics or context to each point. For example, eigenvalue-based shape primitives, angular characteristics, shape distributions, point feature histograms. Modern approaches use deep neural network for representation learning. For example, projection networks, voxel-based methods, 3D convolutional neural networks, and graph convolutional neural network. Feature matching and registration. A popular method for feature matching and registration is random sample consensus, which is also known as RANSAC. It is an iterative algorithm that works by classifying all possible correspondences into inliers and outliers. Iterative point cloud or which is also known as ICP, is a popular algorithm for rigid point clouds. It is also an iterative algorithm that works by assigning the closest points as corresponding points and minimizing square loss for deriving the rigid transformation. Popular approaches for non-rigid point cloud registration are projective correspondence, scene flow estimation, and functional maps. Direct registration approaches combine feature extraction, feature matching, and registration into an end-to-end optimization problem. Some important challenges of point cloud registration are lack of ordering or structure, sparsity, noise and outliers, and partial overlap. Some important challenges of mixed reality are MR headsets have strict compute and power utilization limit for being lightweight and ergonomics. MR experience must also be low latency for a lag-free experience that does not cause motion sickness. Research methodology. Baseline implementation. The first step in our research project is implementing one of the state-of-the-art methods of non-rigid point cloud registration. We choose Leopard. Evaluation of baseline in the context of mixed reality applications. The focus of this project is to study non-rigid point cloud registration in the context of mixed reality applications. We are specifically interested in the Microsoft Hololens 2 mixed reality platform. Most applications of non-rigid applications in enterprise mixed reality involve rigid objects with moving parts. We want to evaluate and identify the computational bottlenecks in the Leopard registration pipeline and mitigate them in the thesis. Development of a fast and robust algorithm for non-rigid registration of rigid objects with moving parts. We want to address the bottlenecks discovered in the previous step in the final stage of the thesis, and the proposed solution should be robust to sparsity, noise, and partial match. Background. Leopard is a state-of-the-art method for partial non-rigid point cloud registration. Point cloud representation. Kernel point convolution, which is also known as kpconv, is used for learning deformable representation without grid assumption. Rotary positional encoding is used to add in positional information, crucial for disambiguation between similar looking parts located in different places. Correspondence matching. A transformer is used for position-aware feature matching. Transformation predictions. For rigid registration, Ransack algorithm is used. For non-rigid registration, there are two steps as follow. Step 1. Rigid fitting with soft procrustes. Step 2. Multiple non-rigid ICP, which is also known as NICP, iterations are used for non-rigid alignment and refinement. Non-rigid iterative closest point, which is also known as NICP. NICP is a popular algorithm for warping a template surface to the target surface. The correct deformation from among all possible warps is obtained by imposing constraints on the deformation, which is also known as regularization of the deformation field. NICP imposes a locally affine regularization that assigns an affine transformation to each vertex and minimizes the difference in transformation of neighboring vertices. The optimal deformation for a given stiffness is obtained by looping over the following steps: estimating, preliminary correspondences by a nearest point search, and calculating optimal deformation of the template for this correspondences and the active stiffness. Motivation. Practical limitations of an ICP. An ICP involves finding a transformation for each point on the source mesh, and the computational requirement can blow up for large meshes. More efficient solutions can be derived for our use case. In this thesis, we focus on non-rigid deformation that happen in the rigid objects with moving parts. Each part moves as a whole relative to the other parts, and so the overall transformation is non-rigid. But at an individual part level, all transformations are rigid. Point-wise transformation calculation is not required under this assumption. If we leverage the part-whole structure of the object, the calculation can be simplified to deriving one rigid transformation per part. Proposed method. Now we discuss our proposed algorithm for non-rigid registration of rigid objects with rigid moving parts. We explain our algorithm with an example registration task on a model of the NASA lunar lander. The source and target point clouds are shown in the figure on the right. In addition to a whole body rigid translation and rotation, the deformable parts like dish pole, sensor pole, sensor joint, and antenna have moved relative to the static component of the model in the target point cloud. Our method begins by constructing a bidirectional graph of the source point cloud, which is available as a CAD model. Each node of this graph represents one of the rigid parts. Each pair of adjacent parts is connected with an edge. In the next step, we run Leopard to obtain the corresponding points in the source and the target point clouds. We show the correspondence matches obtained for some of the lander parts. Next, we derive the whole body rigid transformation for the whole source point cloud. Note that the parts that moved relative to the body, resulting in a non-rigid deformation, could not be aligned in this step. The second step in the tuning process that uses RANSAC and ICP to tightly fit each part in its location in the target point cloud. The area of interest in the target point cloud is determined as an axis-aligned bounding box whose extremities cover the axis-aligned bounding box of the source part and all the corresponding points in the target point cloud for the feature points in the source part. Since ICP assumes that the source and the target point clouds are spatially close, we initialize the ICP algorithm with the transformation obtained from RANSAC. The output of this step is also a rotation and translation for the part in question. The final output looks like this. Experimental setup. We use Leopard models trained on the open source 3D match and 4D match datasets. We test our performance of our approach on the real-world scans of the NASA Viking lander and the Qbot robot model. Now we present the results. The first experiment is designed to demonstrate the best case scenario of non-rigid registration, which is the case of zero deformation and a clean scan of the target point cloud. The source and the target point clouds can be aligned through a whole body rigid transformation. The figure shows the source and target point clouds for NASA Viking lander. The output of registration looks like this. The figure shows the degree of alignment through a map of the nearest neighbor distance between the transformed source and target point cloud. Here are the results for the QBORD model from experiment 1. We observe that our workflow is able to accurately register the source and the target point clouds for the degenerate case of no deformation and low noise. In the second experiment, we introduce a non-rigid deformation in the target point cloud. In the case of NASA Viking lander, the dish along with the dish bowl is deformed. For alignment, we must carry out a whole body rigid transformation followed by a part-wise tuning. This is how registration result looks like. In case of QBORD, the left hand is deformed. We observe that our workflow is able to accurately register the source and the target clouds in the case of the QBORD. We can observe a small misalignment around the deformed hands of the QBORD, as can be anticipated in the case of sparse point clouds. In experiment 3, we consider a slightly more difficult and a more generic version of experiment 2, where multiple parts of the object undergo non-rigid deformations. In case of the NASA Viking lander, the dish pole, sensor, sensor base, and sensor pole are deformed. In case of the QBORD, the left hand and the left leg are deformed. We observe that our workflow is able to accurately register the source and the target point clouds for both the lander and the robot. As in experiment 2, we can observe a bit of misalignment around in the deformed hand of the QBORD, as can be anticipated in the case of sparse point clouds. This is the most difficult setting where we not only have multiple deformations but also a noisy scan of the target point cloud with holes. This closely mimics real-world use cases in a mixed reality applications, where it is common to have holes and missing parts in the 3D scan, like experiment 3. In the case of NASA Viking lander, the dish pole, sensor, sensor base, and sensor pole are deformed. We observe that the results are quite accurate even for this case. In the case of the QBORD, the left hand and the right leg are deformed. There are holes and missing parts in the target point cloud. Just like lander, in the case of QBORD also, alignment is successful. This demonstrates that our proposed algorithm is robust to noise, holes, and missing areas in the target point cloud, and hence is a viable approach for real-world mixed reality applications. Finally, we come to the conclusion of our thesis. Research contributions. In this thesis, we studied non-rigid registration in the context of mixed reality applications. We identified the computational bottlenecks in a state-of-the-art registration pipeline, that is Leopard plus NICP, and proposed a modification for our object of interest, that is rigid objects with moving parts. We also evaluated the proposed algorithms on data collected using Microsoft Hololens 2 and demonstrated robust and reliable performance. Recommendation for future work. The proposed method strongly leverages the structure of the object, which might not always be available. An interesting research direction would be to segment the parts of the 3D object that move as a whole by tracking the movement of the object. This will enable us to use our proposed method for the more generic, non-rigid point cloud registration use cases. Thank you everyone for your attention.